You might be later. That's probably.
It's sweet. I should have asked him before.
What?
Huh. Mm. Damn, I can't even be like, you want me some rice now?
You like.
Hi guys, can you guys hear me? Okay. Okay. I need to make important announcements regarding the exam next week, so I'm going to wait like about 3 more minutes for more people to join, and then I'm gonna go ahead and get started. Can you guys see the screen that I'm sharing?
Yes.
Okay. All right. So, here is a brief announcement regarding the exam for next week. I will post the detailed announcement about the exam tonight. So, every single detail about the exam, you can find it in the announcement section in the web campus. Okay. For now, I'm just gonna briefly explain how the exam is gonna look like. So for the exam, you will need a webcam. Okay. And make sure your computer has a webcam. You will need a scientific calculator, no graphing calculator. Please print out the periodic table. I have uploaded a periodic table for you guys. If you want to use that, you can use that. If you want to print out your own, that's fine too. Make sure you don't have any additional notes on the periodic table that you prepare by yourself. You'd also need a blank scratch paper, okay? And then for all of these, a scientific calculator, periodic table, blank scratch paper, you will have to show it, view it in front of the webcam before you start the exam. Make sure you have absolutely blank scratch note to start off. Make sure you don't have any personal notes on the scratch papers or periodic table, okay? Another thing is find a quiet environment where you can focus on your exam, okay? The exam will utilize something called Lockdown Browser. I'm not sure if you guys are familiar with Lockdown Browser, but what Lockdown Browser is, it's going to during the exam, your exam screen will be locked into the exam screen only. So you won't be able to open any other browser, okay? So it prevents you from hopping around the browsers, so to prevent you from Googling or searching for the answers, okay? And then the lockdown browser system will proctor you, so yourself taking the exam will be recorded, okay? And if there's any movement or suspicious activity, it will be flagged, and I will review your exams recording to see if there's any potential suspicious activities or not, okay? The exam is about 35 multiple choice questions only, okay? And no free response. I recommend you start the exam a little bit earlier, 5 to 10 minutes earlier, because you might experience some problems with lockdown browser, okay? If you experience any problem, do not proceed the exam, but exit the exam screen and let me know right away through email, okay? I have uploaded the study guide on Web Campus. This is a guideline or summary of what we have learned so far. So whatever topic that is not included in the study guide will not be included in the exam, okay? And this is how you can utilize the study guide. You can open the study guide and the lecture note, put it side by side, and I highly recommend you creating your own study guide using the study guide and the lecture note, okay? The study guide doesn't contain any of the practice problems that we solve in the class, but reviewing those and resolving those problems are very, very important. So you might want to include those important notes regarding the practice exercise in your own study guide, okay? And keep in mind that this study guide doesn't contain all of the important things I emphasize in the lecture. This only contains title of the topics that I will be cover in the exam. I will be covering in the exam and the key notes regarding that topic, okay? You definitely have to go back to the lecture note about the topics listed in the study guide and create your own study guide, okay? So that's that for study guide. Make sure you memorize everything that is highlighted in gray color, okay?
Professor Lee,
Mm-hmm.
so for the day of the exam, we're not going to meet here through WebEx.
No, you don't have to join the WebEx. You just have to click on the I think I will put the exam under the quiz tab on Web Campus. I haven't decided where to put the exam, but I think I will put it under the quiz tab on Web Campus. So you just have to click on there and then set up the lockdown browser really quick. I think it should take you only 2 to 3 minutes to set up the lockdown browser and then just start the exam. You don't have to join the WebEx meeting, okay? So do not click on the WebEx tab on Web Campus on Tuesday. Just click on the quiz tab on Web Campus and enter the exam link, okay?
Okay, and I've never used Lockdown Browser before, so am I supposed to like join with your class code or something like that?
It's like a simple software where you download and install. So what was your question again? Do you need?
Yeah, because you say you're going to be able to see the video they take of us, so do I need to send it to you or how does it work?
No. The lockdown browser, the system itself records and saves everything. So it's like a software you install, and that software, it will record your exam, and then it will lock your browser as well, all at the same time.
Okay,
Yeah.
thank you.
Uh-huh. All right, so that's for, yeah.
I'm sorry, I just have one question.
Uh-huh.
So what day and time is the exam? And is the exam going to be like during the class time, or do we have all day until midnight to do it?
During the class time only.
Okay. And then
Yeah.
what days that could be?
It's just our regular class time. So next Tuesday, 1 p.m.
Okay, thank
Yeah.
you.
Mm-hmm. All right.
Sorry, I have a question too.
Yeah.
You said that to start the exam like 5 to 10 minutes early. So what's the earliest that we can access the exam?
15 minutes.
Okay, thank you.
Uh-huh.
Professor Lee,
Uh-huh.
is there a way to have the test due at midnight instead?
Due at midnight? No, I have to set it up at the specific time. And I asked the department and other professors for Gen Kim who taught online courses. They did the same way. So I just want to follow the department's guideline and tradition. Okay. If you have a specific reason that you can't really take it during that time, I can switch the time for you. So you can maybe take it different time during the day, but you have to have good reasons. Okay. Do you have a specific reason why you can't make it that time?
Yeah, I'll be at work. I take the class during work, but I have stuff all over my office that could be considered notes at work. So like at home I don't have this on my walls.
Okay. You can send me email about that, but yeah, I can't make it available all day. Yeah. Just send me an email, see what we can do. Okay?
Okay, thank you.
Mm-hmm.
And professor, will we be having like extra 15 minutes or like 10 just to upload it?
Extra 15 minutes to upload what?
The exam? Do we have to?
Oh, it's nothing uploading or anything. It's just clicking on the multiple choice answers and that's it. You exit the exam screen.
Oh, okay, so
Yeah.
we don't have to show our work.
I mean, you will have to show your scratch paper in front of the webcam, like show what you wrote on your scratch paper, but you don't have to upload anything. Upload a PDF file, upload a Word file. No, you don't have to upload anything. Everything is multiple choice, and you have to complete the exam within the exam screen. You just have to click the answers. That's it. Okay.
Okay.
Uh-huh. Okay, so okay. So last time we were solving this example problems where we were provided the initial concentrations of the reactants and then the equilibrium concentration of the product. And the question was asking us to calculate the equilibrium constant Kc. Okay, again, you cannot use initial concentrations to express the equilibrium constant. Okay, you need to have all concentrations at equilibrium in order to find the Kc. Okay, so we have equilibrium constant of products, so that's good. But we don't have these two, so we need to find these two. Okay, that's what we're going to be doing. Okay. So let's set up a table and write down all the information that we already provided. Okay, we are provided with initial concentration of hydrogen, initial concentration of iodine, and then we are provided the equilibrium concentration of the product. Okay. And then one thing we also know is that because we know the initial, because there wasn't any products in the beginning, we know that the concentration of the product should be 0 in the beginning. Okay, so that's what we already know. So what we need is we need the reactants concentration at equilibrium to calculate Kc. Okay. Since we know the initial concentration and equilibrium concentration of the product, we can find the change in concentration of the product. Change in concentration of the product is later concentration minus initial concentration. Okay, later concentration here referring to equilibrium concentration. Okay, initially the system did not reach equilibrium, but as time goes by, the system eventually reached equilibrium. So I refer when I say later concentration, I'm referring to the equilibrium concentration that the system reached later on. Okay, so if you do that, if you for the later concentration at equilibrium, you have 1.87 10 to the negative 3, okay, minus initial concentration 0. So the change in concentration is 1.87 times 10 to the minus 3. Okay. Note that we put positive sign here. The reason is because this system is depleting the reactants to make product. Okay. You're making the product, so the change is positive. That's why I put positive sign over there. Okay. So since we know the change in concentration of the product, we can use this information to calculate the change of the reactant, two reactants. Okay, so how do we get these two values? All you have to do is use the coefficients. Use the coefficients in the balance equation to relate the change in product and related to the change in the reactants. Okay, so the coefficients for these are 1, reactants are 1, and product is 2. The change, so it's basically 2 mole of product has a change of experiencing change of 10 to the negative 3 mole per liter. Okay, concentration. Then how about 1 mole of H2? How much change is it going to experience? How about 1 mole of iodine? How much change is it going to experience? We just have to do a simple math using these coefficients. Okay, so since the change in product is 1.87, positive 1.87 times 10 to the negative 3, the change in hydrogen concentration is going to be 1.87 times 10 to the negative 3 multiplied by 1 mole divided by 2 mole. Okay, 1 mole of hydrogen. Then you have concentration of 9.35 10 to the negative 4. But you're going to put a negative sign in front of this because you are depleting, you are consuming the reactant to produce product. Okay, so the change is going to be negative. Positive for the product, negative for the reactant and positive for the product. Same thing for change in iodine concentration. Okay, you do the same math, you will get the same value because hydrogen and iodine, they have the same coefficients. Okay, again, this will also have a change in negative sign because you are consuming this reactant, you're depleting this to make the product. Okay, so we have this much of the table completed. We have just figured out the changing concentrations of these reactants. We can use simple subtraction to find out the concentration at equilibrium. Okay, the equilibrium concentration is basically initial concentration say find initial concentration of hydrogen. Equilibrium concentration of hydrogen is going to be initial concentration of hydrogen minus change in hydrogen concentration. Okay, so that's going to be 1 times 10 to the negative 3 minus 9.35 times 10 to the negative 4. That equals to 6.5 times 10 to the negative 5. Okay, so
Wouldn't it be minus negative 9?
yeah, I was just about to explain that. So here, maybe instead of negative sign, you might, this is not like a set equation. This is just the way I'm explaining. Okay, so the equilibrium concentration is basically initial concentration, and you apply the change in concentration. Okay, you're applying the change. Your change is negative, so if you apply the change, you're applying the negative changed value. Okay, so if you are going to get confused here, what you can do is your table, you can have these signs removed. And it's always going to be initial concentration minus change in concentration, if that's easier for you. Okay, I just put the negative sign within the table just to show you that we are depleting the reactants and producing the product. I was just wanting to show you that we're consuming the reactants to make more of the product. I just wanted to show you that the change in concentration is negative, and changing for the reactants and changing the concentration for product is positive. Okay, so here, put a note. You are applying the change. Okay, so before you just follow the mathematical formula or equation, if you're confused about the sign, just take a moment and think whether your reactants are decreasing or increasing concentration over time. Okay, if you started with this concentration, and if you are depleting this amount of concentration, should you have more concentration at equilibrium or less concentration at the equilibrium? What happens if you put a positive sign here? If you put negative, and you have positive, then you will have higher concentration in equilibrium, but that doesn't make sense, right? Because we've been consuming the reactant. Okay, so if you are confused about the sign, just take a moment and think for a moment whether your reactants are decreasing or increasing over time. Okay, so here what we can tell is at equilibrium, we can see that compared to initial concentration, concentrations of reactants decreased at equilibrium. Okay, concentration of product increased at equilibrium. Okay, so now that we have all three concentrations at equilibrium, then now we can calculate Kc. Okay, good. For this equation, your Kc formula is going to be this. Okay, you just plug in all the numerical values into this equation, you will get Kc value of 51. Okay, you can try this math by yourself at home.
Professor,
Yes.
on the exam, will the change concentration be given to us?
Well, so you will encounter a lot of these kind of similar problems, okay? But sometimes the change is going to be given and then you have to find the equilibrium concentration. Or if you are given equilibrium concentration, you should be able to find the change. So there will be a variety of this type of question, if that makes sense.
Okay, yeah.
Yeah.
Thank you.
So this type of question will definitely be on the exam. Yeah. Okay. So far we have focused on observing what equilibrium constant is and how to calculate the Kc value, right? And as we have seen so far, the equilibrium constant is a number that expresses the relationship between the amount of products and reactants present at equilibrium, okay? In a reversible reaction, okay? It is a reaction quotient. This is a reaction quotient at equilibrium, okay? Because the concentration of product and reactants are at equilibrium when we used to calculate the Kc, okay? This is the reaction quotient at equilibrium. Keep that in mind, okay? Reaction quotient at equilibrium. But not only the Kc value is important, but the reaction quotient when the mixture is not at equilibrium is also important. The reaction quotient that is not at equilibrium is labeled as Q. Okay, so this is a reaction quotient not at equilibrium. Okay, to calculate the quotient Q, concentration of product and reactant not at equilibrium, will be used to calculate the quotient Q. Okay, so in order to calculate Kc, you need to have product and reactant concentrations at equilibrium. To find the Q, reaction quotient not at equilibrium, you need to have product and reactant concentration not at equilibrium. Okay, the reaction quotient Q measures the relative amount of products and reactants during a reaction at a particular point of time other than equilibrium. Okay, so this reaction quotient Q helps us to figure out which direction a reaction is likely to proceed towards equilibrium. Okay, so K versus Q. The main difference between K and Q is that K describes a reaction that is at equilibrium. Q describes a reaction that is not at equilibrium. To determine Q, concentration, pressure, concentration. So it can be either QC or QP. Okay, so this is in terms of concentration, this is in terms of pressure. Okay, concentration or pressure of the reactants and products at any given time during a reaction is submitted to the equilibrium expression. Okay, so K and Q basically have same formula: concentration of product over concentration reactant. But K is concentration at equilibrium. Q is going to use a concentration at not at equilibrium. Okay, again, why is Q important? Comparison of Q with K indicates which way which direction the reaction shifts. And which side of the reaction is favored towards dynamic equilibrium. Okay? That's why comparing Q with K, comparing Q to K is important. Okay? Let's take a look at the example. So not all chemical reactions out there are reversible, but for those that are reversible, we want to achieve the equilibrium. So the nature wants reaction quotient to be a quotient at equilibrium. Okay. And as I just mentioned, the reaction quotient Q can be used to predict the direction of reaction towards equilibrium, right? But how? So if a reaction quotient at any time is smaller than K, equilibrium constant K, the reaction will proceed towards equilibrium by making more of the product. Let's say so this is product reactant. Okay, let's say for this system, when not at equilibrium, the Q value is 0.5. And let's say for this reaction at equilibrium, the K value is 1.1. Okay. The only way for this system, this reaction, to reach equilibrium and Q becomes equal to K is by increasing the numerator value. The only way Q value can equal to K is by increasing the product concentration. Okay. So in this case, the reaction will make more product in order to reach dynamic equilibrium. I'm going to write that down. The reaction will make more of the product to reach dynamic equilibrium. Okay, so the for reaction proceeds to form more product. Okay, and the when Q is equal to K, the reaction is in equilibrium. When Q is larger than K, the reverse thing will happen. Now let's say the Q value is 2.5, and let's say K is 1.1. Okay, the only way the only way Q become K, the only way the reaction can reach equilibrium is by reducing this number or by reducing the concentration of the reactant. Okay? Oh, I'm sorry. Increasing the concentration of the reactant. You need to increase the denominator value. Okay? In that way, Q will decrease and it will be equal to K eventually. Okay? So in this case, the reaction will make more reactant in order to reach the dynamic equilibrium. The reverse reaction proceed to form more reactant. Okay? All right. Let's try a sample exercise. At 448 degrees Celsius, the equilibrium constant for the reaction. Okay, I don't know why this arrow is at the bottom. Okay, so the equilibrium constant for the reaction is 50.5. So Kc is given 50.5. Predict in which direction the reaction proceeds to reach equilibrium if we start with 2.0 times 10 to negative 2 mole of the product and 1 times 10 to negative 2 mole of hydrogen and 3.0 times 10 to negative mole of iodine in a 2-liter container. Okay. Okay, so we are given the initial concentrations. Okay, so this is a concentration not at equilibrium. Okay, so the initial concentrations oh, they didn't give us the concentration, they gave us the mole. Okay, and because we are provided with a volume, we can easily find the concentration. Okay, so let's find the concentration first. For initial concentration for product is going to be the number of mole given. You're going to mole per liter, so divided by 2.00 liter. Okay, that's going to be 1.0 times 10 to negative 2 mole, or mole per liter. Okay, concentration, initial concentration of hydrogen is going to be 1.0 times 10 to the negative 2 mole, 2 liter. You will have 0. You don't want to use 0.5 for the scientific notation, so I'm going to change to 5.0 times 10 to negative 3 mole. Concentration of iodine is going to be 3.0 times 10 to the negative 2 mole divided by 2 liter, which is 1.5 times 10 to the negative 2 mole, or mole per liter. Now that you have all the initial concentration, you can find the quotient Q. Okay, it's going to be, we want to put C because we're working with concentrations. It's basically concentration of product raised to the power equal to the coefficient divided by concentrations of reactants. Okay, so that's going to be 1.0 times 10 to the negative 2 square divided by 5.0 times 10 to the negative 3 times 1.5 times 10 to the negative 2. That's 1.3. Okay, so we have QC of 1.3 and KC is 50.5. So we know that QC is way less
Professor,
than.
can you slow down a little bit?
Oh, okay. So did you get this part?
I'm still writing that part down.
Okay. Okay, so as we know that QC is only 1.3 and KC is 50.5. The question is asking us to predict which direction the reaction is going to proceed. Okay, so this is a reaction quotient in the beginning. Okay, so it's asking how can this reaction reach equilibrium, by producing more product or by producing more reactant. Okay, so in order for QC value to reach KC or increase up to KC, the numerator has to increase. Okay, the product has to increase in order for this reaction to reach equilibrium. Okay, so the reaction proceed to make more products. The reaction proceeds to make more products. For what? To reach equilibrium. Okay. The reaction proceeds to make more product means the reaction proceeds to right side of the reaction. Okay. I don't have time, so I'm just going to skip this exercise. Okay, so we're going to try another type of derivative problem. Okay, in this problem, you are provided with equilibrium constant K and the initial concentrations. Okay, you are asked to find the equilibrium concentration. Okay, that's the type of exercise that we're going to be doing in the next few slides. This is very similar to the previous problem that we did, where we were provided with the equilibrium concentration of the product, initial concentration of reactants, and we were asked to find the equilibrium constant, right? So it's like a little switch around here. Okay, so similar approach to the previous problems are going to be used when, and you always want to find the change in concentration. Okay. And these change in concentration will have the same coefficients as in the stoichiometry, or as the PowerPoint slide says, it will simply be a factor of x based on the stoichiometry. Okay, let's try the sample exercise. Okay, 1 liter flask is filled with 1 mole of hydrogen gas and 2 mole of iodine gas at 448 degrees Celsius. Okay, Given a Kc value of 50.5 at 448 degrees Celsius, what are the equilibrium concentrations of reactants and product? Okay. So again, you are provided with initial concentration of hydrogen and iodine. Okay, and then you are provided with Kc information. You need to find equilibrium concentration of all these three. Okay, so the first step will be creating a table again. Write down all the information that you already know. Then you put, so we already know the initial concentration, so we put 1, 2, and because we have 0 product to start, so we put 0, okay, for the initial concentration of product. Then we put X to indicate the change in concentration, okay, and again, this change in concentration will have same coefficients as in the balanced equation, okay, so the change for the product is going to be 2x. For iodine, it's going to be 1x. For hydrogen, it's going to be 1x. Okay? Negative sign indicates that you are using the substance, you're depleting the substance. Positive sign indicates that you are creating the substance. Okay? Positive change, negative change. Okay? Since you are using the reactants to create product, reactants, hydrogen and iodine will have negative sign, okay, and product will have positive sign, okay. Second step should be filling up the section for the equilibrium concentration. Again, equilibrium concentration is basically a later concentration. So to calculate the equilibrium concentration, you take the initial concentration, and apply the change in concentration occurred. Okay, so it will be initial concentration 1, apply the negative X. Okay, same for iodine. Oops, initial concentration 2 mole per liter, apply the change, the negative change. Okay, same for product, equilibrium concentration, initial concentration 0 plus 2x is going to be 2x. Okay, so these are the equilibrium concentration expression. Okay, so if we substitute the equilibrium concentrations into the equilibrium constant expression and solve for x, we will get the x. Okay, so here I basically substitute 2x for the equilibrium concentration of product, 1 minus x for the equilibrium concentration of hydrogen, 2 minus x for the equilibrium concentration of iodine. Okay, and if you do all the math, I don't have time. I was going to show you, but I don't have time, so I'm going to skip that step. It's just a quadratic formula, and you might want to be familiar with the quadratic formula for the exams. Okay, so solve for x using the quadratic formula. You will get x of 2.323. Okay,
or you will get 0.935. So which value do you have to use? Okay, you're going to plug in X to find the actual value of these equilibrium concentrations, right? So what value do you want to use? Since X must be subtracted from 1 molar in order to find concentration of hydrogen, the number 2.323 makes no physical sense because negative concentration doesn't make any sense. Okay, so the value that you will choose that makes more sense is going to be the value lower than 1, which is 0.935. Okay, so you just basically have to plug into the equation where it says 1 minus x, you plug in x, and then you will get this. 2 minus x, you get this. And then 2 times x, you get this. So you have finally found the equilibrium. You see here, equilibrium concentrations for reactants and the product. Okay. Now that we have good understanding of what an equilibrium reaction is and what equilibrium constant represents, we need to think whether do we always want an equilibrium reaction? Okay. How about a case where the nature of the reaction is the equilibrium, but you don't want the equilibrium reaction? Can we manipulate or control the equilibrium reaction? The answer is yes. Okay. According to Le Chatelier, he stated that if a system at equilibrium is disturbed by a change in temperature, pressure, or concentration, the system will shift its equilibrium position to counteract the effect of the disturbance. Okay, so if we want to manipulate or shift the equilibrium reaction, we can change either temperature, pressure, or concentration of the substances. Okay. So in next few slides, we will take a deeper look how concentration, pressure, and temperature affects the equilibrium reaction and how and why these factors can switch to equilibrium reaction. Okay. So first of all, changing the concentration of the reactant or product can switch the reaction to equilibrium. And here is the Haber process. Not sure if you can recall. This is the Haber process. This reaction is equilibrium in nature. Okay, so in a closed system, this reaction would love to stay at equilibrium. That's where this reaction is comfortable at. However, let's say we want to produce a lot of ammonia and sell ammonia to make money. Do we still want this reaction to stay at equilibrium, or do you want to produce more ammonia? Of course, we want to produce more ammonia, right? So in order to produce more ammonia, we need an external factor to push the reaction to the product side. Okay, and one thing you can do is keep adding one of the reactant, and this will push the reaction at equilibrium towards the product side, producing more ammonia. You can either increase nitrogen concentration or hydrogen concentration. Okay. If you increase both reactants, you're basically scaling up the reaction, and that's not going to push the reaction towards the product side. Okay, so and another thing, number one thing you can do is keep adding one of the reactant to make more product. Another thing you can do is you can keep removing ammonia that is being produced. Okay. Another thing you can do is you can keep removing the product, keep removing the ammonia, and this will also push the reaction and equilibrium towards the product side. So these two things will both push the reaction to right side. Okay. So to sum up this concept, any substance that has been added to the reaction will be used up in the reaction. Okay, because you added the nitrogen, you added more of the nitrogen, the reaction will proceed to the right to use up that added nitrogen. Okay, any substance that has been added, it will be used up in the reaction. Any substance that has been removed will be produced more in the reaction. Okay, now that product is keep being removed, the equilibrium shifts toward right so that it can make more product to stay at the equilibrium. Okay, if we want to relate this concept to quotient K, quotient Q, let's say let's say with more reactant added, you are adding more reactant. So scenario 1, if you have more reactant added, you're going to increase this portion. You're going to increase this portion. Okay, then the Q, reaction quotient Q, will change. Is Q going to be larger or smaller? Now, if you increase this, the Q is going to be smaller than K. Okay, so what did we observe here? If Q is smaller than K, the reaction proceeds to product, right? Therefore, the reaction shifts to right, and we can make more ammonia, and we can make more money. Okay. So one thing to keep in mind is that the reaction quotient Q is what's fluctuating. Okay, when you are changing the concentration, K will always have the constant value unless you change the temperature. Okay, so K is always there. K value is always there. If you fluctuate the concentration, this Q value will fluctuate. Okay, and then you can find out the Q value, compare with the K, and then determine whether the reaction is going to proceed to the right side or to the left side. Okay. Okay, the second external factor that can change or disturb the reaction equilibrium is volume and pressure. Okay, when gases are involved in an equilibrium, volume and pressure can alter the reaction equilibrium. Okay, if volume is, let's say volume is decreased, okay, then pressure is increased. Okay, volume is decreased and then the pressure is increased. Then what happens to the equilibrium system is that the system will shift to a position that it can reduce this increased pressure. Okay, in a simple way, think of a situation with extremely high pressure. A system with high pressure would want to release that pressure. Okay, so if your system has pressure increase, it will want to release that pressure by shifting the equilibrium to release the pressure. Okay, so how can a reaction system release the pressure? The system can alleviate the increased pressure by forming less mole gas. Less mole of gas. Okay? It's basically if your room is too crowded, the volume size of the room decreased, the pressure increased. If your room is too crowded, you kick people out. You reduce the number of people in the room. That's what the system's going to do. It's going to shift to the reaction direction so that it produces less mole of gas. Okay? Let's say we're performing a reaction where 2 mole of A produce 1 mole of B. Two mole of A produce 1 mole of B. If you're dealing with a situation where volume of the container is reduced and the pressure is increased, which direction do you want the reaction to go? The direction to have more of the 1 mole of B, or direction of 2 moles of A? Okay, the answer is the direction to have 1 mole of B is the answer, because then your container will have less mole of gas and less crowded. The increased pressure is then relieved. Okay, so in this situation, if your pressure is increased, you're going to shift, the reaction is going to get shifted to the right, because the system would want to produce less mole of gas. Okay, if the reactions shift to this side, you will only create 1 mole of gas versus 2 mole of gas. Okay. Okay, I'm running out of time. So the details about endothermic and exothermic reactions are not going to be included in the exam, but I will explain this regardless because you need this information to finish your homework. Okay. One important thing to note is that only temperature will change the K value. Okay, so the previous examples where you fluctuated the concentration, where you fluctuated the pressure or volume, those will only affect quotient Q. K value will not be changed. But if you change your temperature, this will change the K value. Okay, so keep this in mind when you do your homework. Kc and Kp are constant at constant temperature. Okay, these are the constant at constant temperature. So they will vary as the temperature changes. Okay, so for endothermic reaction, you will have positive enthalpy, so positive delta H value. In this way, if the heat is going to be consumed. Okay, so this is how the equation for endothermic reaction should be like. For exothermic reaction, you have negative enthalpy. You produce heat. Okay, and then you need to remember that for endothermic reaction, heat acts like a reactant. Exothermic reaction, heat acts like a product. You see, heat is on the the reactant side for endothermic reaction. Heat is on the product side for the exothermic reaction. Okay, if you have these two information, you can solve all the homework problems problems no problem. Okay, so let's say if the heat is added to the endothermic reaction. Okay, heat added to endothermic reaction. Okay, is the reaction going to shift to the right or left? The answer is reaction shift to right. Okay, K value is product over reactant. Okay, so okay, I didn't explain. Why is it shifting to the right? You basically treat heat as a reactant, right? What happened when you added more reactant? When you added more reactant to a system, the system would want to use up that added reactant, okay? So that's why the reaction is going to proceed to the right, okay? And in terms of K value, whether it's going to increase or decrease, you can evaluate from this concentration expression. If your reaction is going to the right side, your product concentration is going to increase. Okay, so this will result in increased K value. Okay, so if heat is added to an endothermic reaction, the reaction shift to right, and you will have increased K value. Why? Because of this. Okay, let's take a look at another scenario. Let's say heat is added to exothermic reaction. Okay, if heat is added here, what's going to happen? The reaction is going to shift to the left side because you want to make more reactant with the amount of heat added. Okay, so in this case, reactant concentration is going to increase, and then what's going to happen to the K value is going to decrease. Okay, I think I will have to end the lecture material there because I really want to go over this one homework problem that I think you guys will have problem with. Okay, so I'm going to quickly show you guys how to solve that one. It was okay. It was one of the questions with title Re-establishing equilibrium. Okay. The question, let me see if I can find the question number. It was question number 25. It was question number 25. Okay. for this question, you had this equilibrium balance equation. Okay. And the concentration were given. And this is a scenario where if more nitrogen oxide is added, changing the concentration to certain value, okay? So 0.200 mole, and this is 0.7 mole. Change okay. My numbers and your numbers will be totally different. So, but if I show you how to solve this, you can easily solve your own homework with your own value too. Okay. So the question is giving us the initial concentrations. Okay. Oh, this is a concentration at equilibrium. Okay. And then now it's adding more nitrogen oxide and it's disturbing the equilibrium. Okay. Once you disturb the equilibrium, the system will try its best to re-establish a new equilibrium. Okay, so if more, this is a scenario where when you add more nitrogen oxide, and if the concentration is changed, what will be a concentration of nitrogen oxide after equilibrium is re-established? Okay, so first of all, you need to find Kc. These are the concentration at initial equilibrium, so you can use this information to find the Kc. Kc is basically this. If you plug in the numbers, you will have Kc. Okay. If you add nitrogen oxide, what would happen to an equilibrium? Will the equilibrium shift to the left or shift to right? If you add nitrogen oxide, the reaction will want to shift to left because you want to utilize more of the product that's being made, okay, or you utilize more of the nitrogen oxide that's been added. Okay, so the reaction is going to shift to the left. Okay, so then I'm going to create a table with new concentration. Okay, okay, so with the new system where more nitrogen oxide is added, the starting concentration is 0.7. This is the final is second equilibrium. 0.7. We did not make any changes to the concentration of nitrogen and oxygen, so there's still 0.200 mole, 0.200 mole. Okay, now the change here is no longer positive here. Positive here. Now that the reaction is going to the left side, you are actually depleting the nitrogen oxide. So the change here is going to be negative 2x coefficient. Okay, and now the reaction, because the reaction is going to the left side, you are making more of the nitrogen and oxygen. So the change for these two molecules is going to be positive. You're generating them. Positive x, positive x. Okay, so then the final concentration after the second equilibrium is re-established is going to be 0.200 mole plus x. Or let me take out the 0.200 plus x, 0.700 minus 2x. You apply the change. Okay, so then what would be the new case? Kc? Not new Kc. You're not changing the temperature, so Kc will always be the same, right? So Kc is same regardless. Okay, unless temperature change, right? So Kc is same regardless. So let's write equilibrium expression using these new expressions that we found. Okay. Is equal to the initial Kc value that we found up here. Kc value will always be the same. Okay, so now what we have to do is we have to solve for x. If you solve for x, this is a very, very just simple math. If you solve for x, you're gonna get your x 0.0750 mole. Okay, so then if you plug this x into here, you can find equilibrium, second equilibrium concentration for this. If you plug in here, you will find equilibrium concentration for this. Plug in here, you find this. Let's say you want to find the final nitrogen oxide concentration after equilibrium is re-established. Then you take 0.7 here, 0.700 minus 2x, which is 0.700 minus 2 times 0.0750. That math is going to be 0.550 mole. This is going to be your concentration for nitrogen oxide after second equilibrium has been established. Okay. Okay, I'm sorry for going over time, but yeah. So I'm going to end the lecture here today. I'm going to hang out for another 5-10 minutes just in case anybody else has questions. And the lecture note, this lecture PowerPoint with my notes on it, will be uploaded on Web Campus tonight. Again, the detailed information about the exam is going to be uploaded on the announcement section tonight as well. So please check those two. And then, yeah, if you don't have any questions, I'll see you guys next Tuesday. And if anybody has questions, you can unmute your microphone and just ask me. Okay?
I have a question.
Yeah, go ahead.
For the change in the homework question you were just going over, where did you get the x and the 2x from?
Change?
Oh, it just changed. So how did you get the 2x? Is that just from the 2?
2, yeah. So
okay.
yeah, keep in mind that you always have to use the coefficients in the balance equation. Okay?
Okay.
Because if the 1 mole change of oxygen is going to be related to the 2 mole change of the nitrogen oxide. Okay, so the change will always have same coefficients as the balanced equation. Okay,
Okay, thank you.
yeah, let's keep that in mind.
Professor, how do you find 4 for the KC?
4 here, here. So
Was that given to us?
given to us. So if you go back to your homework and read it, they said this is the initial concentrations at initial equilibrium. Okay. So then using this information, because we know that these concentrations are concentrations at equilibrium, we can use these values to find the equilibrium constant for this system, correct?
Right,
Yeah.
and we could use our KC to figure out what X is later on.
Yeah, because so what happened was that you initially already had equilibrium system, but then they added more nitrogen oxide, they disturbed the equilibrium. But after the disturbance, what's the reaction's gonna do? The reaction's going to try hard to re-establish the equilibrium, right? So once the second equilibrium is reached, the Kc value will still be the same. Equilibrium constant is always the same, right? So you can use same equilibrium constants for the second equilibrium situation as well too. Does that make sense?
It does. Thank you
Yeah.
so much.
Mhm.
I just have one question.
Mm-hmm.
So how do you know that the reaction shifts to the left? I just want to double check because I don't know how you were able to figure out if it's +2 or -2.
Oh, okay. Again, if you are adding more nitrogen oxide, do you want to use up the nitrogen oxide or no?
Yes, because if it's
Yeah.
added to the reaction, right?
Yeah, if you're
It's gonna
added,
be used in
yeah, the PowerPoint says that if you add a substance, the reaction would want to use up that added reactant, right? So here the situation is nitrogen oxide is added more to the reaction. It's added. So what's the reaction going to do? It's going to use the nitrogen oxide. How do you use nitrogen oxide? By shifting the reaction to the left side. Make sense?
Okay.
Yeah.
It does make sense.
Yeah,
Thank
and
you.
then this negative sign, for the negative sign, just take a moment and think to yourself, am I creating nitrogen oxide or am I depleting? Am I using up the nitrogen oxide? Here, yeah, so
it's
here
negative.
you are using up the nitrogen oxide because you have so much nitrogen oxide coming in, now you have to use it. So if you're using it, if you're depleting it, you put negative sign. Is that clear?
Thank you. That makes a lot of sense. Yes.
Mm-hmm.
Thank you so much.
Mm-hmm.
And why do we need the Kc value?
What's that again?
When we get the Kc value of 4, what do we use with it? What do we do with it?
What do you mean what do you do with the Kc value?
Why did we find it?
Sorry, I don't understand your question. Can you elaborate your question? Hello?